We are going to look at the topic that occurs when we have um, algebraic loops, when we have difficulties with making the model. So let's take a look at an example on this presentation about how do we go about solving that problem and what should we do to avoid it. So here we go, and we close out of here, and this is the outline of what I'm going to talk to you about. To give you a little introduction, what are the nature of algebraic loops? I want to talk to you about the understanding the constitutive equations of algebraic loops, and then how do you generate a CAMG model that has algebraic loops. Then the next topic we'll look at is how does the solution is of algebraic loops are using KMG, and how it automatically detects explicit state space form once we discover the difficulty, and then how we go about creating some auxiliary matrices to be able to solve this problem. And finally, concept I think is probably the most important on this topic is what is the physical meaning of algebraic loops? Why do they happen? So let's take a look at an example here. And we have in here an electrical circuit. Yeah. If you put this electrical circuit and you create this model, you have what we have on the bottom here. So in here, what happens is that um, if we could look at the system in here and assign the causality, you will realize that we end up with a situation where the causality does not complete. So you see here there is a loop here, there's another loop here, and a third loop, so we have the ones in there. As a first step, we put this element R over here, this one over here, and this over here. We put the C over here, and following the procedure for creating the bond graphs, which we have established in previous lectures, we use the zero junctions to model the elements in between, and then we assemble it. So you see this path, this causal path between 2, 3, 5, 4, 6, 7, and 9, and even 10 is totally undefined. This situation we did not encounter before in any example that I gave you. But wouldn't you say that the model really is not something that is out of the other world, or extremely complex? It looks like a very innocent circuit, yet it has the way we have connected things produces this problem. If you still are a little bit unsure as to what I'm talking about, what I would do is, let's run the CAMG software and put this in so you can see what the problem is, okay? So let me just bring it up in here. We will see it's over here, and then I'm going to say, okay, I am going to enter this bond graph model that I see here. Let me just see if I can put this down here. This, I'm going to close it. I basically would like to have the bond graph model on my left hand side, and then in here I'm just going to enter it, because it's possible that still somebody who is looking at this is not sure exactly what's going on. So let's just draw it. See, you put the SE, and then I put the one junction over here, and pretty soon you'll realize how this happens. And then I put the R element over here, and then I put the 0. This is, of course, when you entered it into the CAMG software, you are not thinking on how to make the model, but rather you are just transcribing the model to the system. See here? Okay, so first, it was red. Now it completes this, and it looks okay again, because CAMG calculates the causality and the power flow as you have entered as it goes. See, immediately it shows this red path in there. This red path, it means something does not complete, cannot complete. Something is funny about this. So in here, I am gonna put the other. In this case, of course, because it does, we cannot leave one junction open. Here's the first sign of trouble. Do you see how this thing is red, all this path in here? And we completed an element on the 1. And then we go over here, and then still nothing. We put the I element over here. Yeah, that looks all right. And so there's some hope that the system like that would work just fine. No problem. Now all of a sudden we add 1, and it's bad again. We put the R element in here. It's really bad, because now the one entire section of the bond graph is red. And then we put the C element in here. It did not help at all. So this is the problem. What I would, CAMG is telling you, when you see a path like this red, it's like a flashing red light. It says, stop for a moment and think about what's going on. Maybe the system is not very well assembled, or if you really insist the way it should be like this, you are looking at an implicit solution of the equations. And that also is not very good. So we have to find a way to solve this. Just for purposes of illustration, we say verification, if you will. Why don't I assign the causal marks in here? And I'm gonna do it with a red pen so that you can see what's happening. So I'm just gonna do it by hand. Blue pen, I want a red pen. So if we assign it to the sources, see right there, we say, okay, the source in here, good. I assign integral form to this one. All right, so this is like that, no problem. And then I assign another I element over here. Yeah, and then I even assign this one in integral form. No problem. And then can I progress over here? No. Can I make some progress over here? No. Over here? No. And here? No. Do you see the problem? I cannot assign the causal marks on any of this stuff. And that's what the problem is here. And CAMG is telling us, is telling us even in more explicit way by leaving the elements in red form, like you see over here. Okay, so now that you have seen the problem in the sense of the producing the system, let's understand a little bit more what's going on in here. We start with a system like this, right? Think about what would happen if you assign the causality here. You assign, because by default the graph does not lend itself for that, but rather you say another element can take either one of the two causal forms, so I could assign. And in fact, where is the little drawing I did? Yeah, right there. If you assign it like this, say over here, let's say you say, oh, I'm going to do with blue the ones that I arbitrarily assign, okay? But I assign it not widely, but arbitrarily, meaning I could help this by assigning this, and then this will complete because this would go like that. But you see, if you have it like this, then this also would go like this. See? All right, so this part of the bone graft model is fixed. But can I do anything over here? No. So this is still is a problem. So in here, what I'm trying to show you on my slides here is that you can assign here the E sub 2 and you fix it up to here. But you have an algebraic causal path in red over here. But this one here, if you could assign here, then when you assign it this way, everything falls into place. And in this here, if you assign it here like this, you would have to assign also in here another one to be able to complete. So you make, in this case, F2 as the assignment, and in this case, you will have to do 2 assignments. Still, this is, it is a difficulty. Let's understand the constitutive equations of algebraic loops. In this case of the, if we assign it like this, and you producing using CAN-G, QU, you will get these equations. The problem is that if you substitute these equations into these derivatives like that, you will not get explicit form. In fact, you try and you're gonna get this. See, you'll get the dp sub 4 and dp sub 8, dq11. Here, these are the equations you will get like that. And you cannot get rid of this F2. You try it and it keeps coming back. So the way to do it is just like when you say take the bull by the horns. Here you have F2 would be a separate equation in terms of the state variables and the inputs to be able to solve it here. So the answer to the problem here is that we have the 3 differential equations, but we need this auxiliary equation. Okay, so in the case of the 2 loops, you see, in the first case, you get the derivative, you get the Cauchy form of the equations, and it doesn't matter how much you try, you will get E2 on the right-hand side and F6 on the other 2 equations, and you can get rid of those. So we should define an E2 and an F6 as a functions of the states and the inputs. And if you define that E2 and F sub 6, then you have a system to be able to solve. So this is the case with 2 algebraic loops. And these are like output equations that we have. Okay, so now let's take a look at the CAMG solution of the algebraic equations. This is what you have. This is what I entered a moment ago, and this is the way it is. It has all three of those. Now, notice here on the if we assign this, we might be able to do this. If you assign the causal marks in here, if you assign it here, you'll solve one of these. And if you assign to the other, you will solve this whole thing. Okay, so the answer to this dilemma is once you have mathematically here, once you have the Cauchy forms and you realize you have these variables that you cannot get rid of it, you have to define those in terms of the state of the state's variables and the inputs. And instead of solving these three equations, you have to resolve these five. That's how you solve it. But in the case of, in this case right here, when you have a larger bond graph model, you find all these causal paths. So you are talking about 1, 2, 3, 4, 5, 6, 7, 8 of this. This would be very tedious to do. So one solution here is that you have the derivatives and the auxiliary equations in here, and then of course these are the output equations. This is the initial state space form, but you see there are these auxiliary variables that I would call them that are needed to solve this. So in order not to confuse with the matrices names that I use for algebra, for derivative forms, I'm going to say this is the initial A plus the initial B plus this J matrix multiplied by the vector A, small a, this vector would be the vector of these auxiliary variables. So A is a vector that is also in terms of the states and the inputs, and of course in terms also of the A variables. So you could see that equation number 4 shows you the problem. This is not explicit form. See, it has the vector A here, and it has the vector A over here. So I have set up a way, basically you may say I translated these equations into the set of matrices. And you see this E2 right there, and this F6, that's what this A is. And then I say A, so E2 and F6. So these two equations that you see right there are these equations right here. See? But you cannot get rid of the variables. You see E2, you see F6 on this. F6 over here, you see E2 over here. So that's what we have in here. So looking at this, I propose the following solution. Let's move that A to the other side. multiplying it by the identity matrix so that we can solve it with this M. And then you have K and L with the states and the input vectors. Multiply by the inverse of this. It's a similar operation we did to get rid of the derivative form, and we produce these matrices. Once the loops are resolved, then the system A and B matrices can be calculated because this A now it's is calculated in terms of the states and the input. So what I did is in this original form that you see here, right there, this one. I first figured out what the A was, and now I'm replacing it in here. See here, replace A, and then we put all those matrices in here, and then I use the factor of this. You could see that the new A matrix is very complex. This one right here. Maybe I use my other pointer here to illustrate. The new A matrix is this part. The new B matrix is this. And then, of course, the A matrix can be calculated like this, and the B matrix like this. And then finally we get the new state model. But it takes a huge amount of matrices to be able to do this. So in the output matrices, because we have Y, and Y will have also this A of the variables. We know now what A is. We found the solution for the algebra loop of the auxiliary variables above, and we use this and we plug that A into this equation. In other words, this A here, this in here, and then we calculate Y. So the new C matrix is going to be this one, and the new D matrix would be this until we produce it in the way we want it. You can see mathematically, this is, of course, provided that the coefficients are not variables that will produce unstable numerical solutions. If the coefficients are constants, then of course this is a good solution. But we have to be careful, huh? So in this particular case, I calculated the new A matrix for the first example that we had. And of course you could see it becomes more complex, but you can do it. So that's the A, the B, and the C matrices. Now, if you do a transfer function under the circumstances, remember that using that expression based on the matrices, you can actually produce the transfer function. So you could see in this particular case, produce the transfer function between two of these variables in here using these matrices. You see I put it in yellow here. S is cubic, is fourth, this is S, and then the constant term. If you put some numbers, you'll get something like this: E11 over SE1 and E6 over SE1. So once, and then of course you could do the step and input response, and then the frequency domain, do the body plots. Yeah. Finally, okay, we have proposed a solution, but like I said at the beginning of my presentation, let's look at the most important part. What is the physical meaning of these algebraic loops? To do this, I have chosen this a model of a valve in an engine, as one of those valves, the intake or the exhaust valve, that has all these components. It has the spring, and it has the valve itself, and it has a camshaft that drives this. So this is the modeling here. So here's the cam, and then there is the model on both of these springs, both sides, and that's what you have on the right hand side. So in this particular case, this valve spring model, let's say, take a look here in this. Okay, it has 6 masses in there. If I actually try and I do this like this, I take the mass away, and instead I just connect these two together. You see what happens on the right, on the bond graph model. If I suppress the eyes, you create two algebraic loops on the equations. So I think if I can drive my point home is this. This system looks normal, right? The system looks like you have done a very nice job considering all the parts in here. This one doesn't look too normal. Either there is only one of these, not two of those connected in this funny way. Because if I do this, all I have done here is suppress these two I elements over here, and bingo, I have this algebraic loops. All right. If you keep doing this, and I do it to the bottom of this, you see how the algebraic loops appear? I think the point here is this. The way we connected the parts produce these algebraic loops. So always we should take a second look at the system itself. And in this case, the author of this famous textbook, the one that you have here for the modeling of mechatronic systems, Professor Carnot, he says, when you have a derivative form or you have an algebraic loop, the best solution is for you to review what the system is, or whether you consider an element too many, or you are not considering an element that should be in there. So I think that algebraic loop and derivative causality, we can solve them. And I think having the tools in MATLAB and CamG being able to produce even the equations with algebraic loops then gives us the opportunity to solve those using the computer and solve a set of equations that otherwise would be implicit to be able to solve this using the CamG software. So it is possible to do it. It's just that it is, you induce a harder solution. So if we reach this conclusion, we say that it is possible to do a computer-generated solution of algebraic loops. We can do a single algebraic loop system, or we can do multiple algebraic loops, as you have seen. The solution is independent of the system order and also of the number of algebraic loops. It could hold for both of those conditions, regardless of the order or the number of loops. The solution is valid for linear and nonlinear systems, provided that we are able to specify those matrix coefficients. opens the door for the solution of a new set of systems and integrates both of these technologies, the classical Bullock diagram and the bone graft models. And of course, the solution is integrated by using ChemG and MATLAB. Okay.